Assalamualaikum and very good morning. Today I will present our group projects, which is for group assignments for design optimization (BMCG) for 4343, which is topology optimization of the back crank levers, which is in our agenda. We will discuss more about introduction, methodology of our projects, and the result and discussion, and lastly a conclusion. So, what is topology optimization? Topology optimization, a mathematical technique for optimizing the layout of material inside a given design area. It distinguishes from form and sizing optimization in that the design can take on any shape inside the design space, rather than being restricted to predefined configuration. So, our topology optimization is a bell crank lever. Bell crank lever is a rigid body to attach it to and capable of rotating around a point called the fulcrum. Used to lift heavy loads with a minimal efforts, and the ratio of the burden lift to exertion is referred to as a mechanical advantage. Used in various industries such as automotive sector, manufacturing, and household. From the picture here, the circle shows the where is a bell crank lever. Let's continue the software used in topology optimization for our group assignment. So the software used first is SolidWorks. SolidWorks is a solid modeling computer at the design and computer at the engineering program. At the initial stage, the software is used for planning and visual ideation, modeling, feasibility assessment, prototyping, and project management. Used by mechanical, electrical, electronic engineer to form a connected design. And the second software that's used in our project is ANSYS, used to simulate computer model of structure, electronics and or machine component for analyzing strength, toughness, elasticity, temperature distributions, electromagnetism, fluid flow, and other attributes. Used to determine how a product will function with these different specifications without building test products or conducting a crash test. And then lastly is Cura. Cura is a slicing software. It is an open source software, probably the most widely used in the global additive manufacturing market. Support for different file formats and compatible with many 3D printing. So, our project objective is to create a bell model crank lever using a SolidWorks software, and to optimize the bell crank lever model using assist software topology optimizations, and to create many variety material of the functional structure bell crank lever. Lastly, to utilize 3D printing to fabricate the optimal bell crank levers. For the methodology chapter, we will continue to the Haziq Diniy. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Mohamad Haziq bin Halim, and today I will present about the chapter 2 will be the methodology of the procedure from drawing design until topology analysis. So we use SolidWorks for making the design of Balkan level. So you mean that Balkan level we can found from car, and we actually following the scale of the Balkan level car and apply into a drawing SolidWorks. So will 100%ly this will be the Balkan level cup according to the spec given. So after the step 1 will be the drawing of the CAD file. So the second will be the using the software of ANSYS. Here we show that the A diagram shows the input of the static structure, and the B will be the topology optimization. So this is our analysis, FPA, finite element analysis, which will be the geometry diagram, and we can change our type of material. That we use 4 type of material. First will be the structure steel, second stainless steel, third will be grey cast iron, and lastly will be the titanium alloy. So this part, the first step will be the insert the geometry, and then we will use mesh to make sure the element of the part includes, and now surface plane material. So the static structure we will start with the applying the bearing loads. So the bearing load here, so application the bearing loads, we assume that the x-axis, the front here will be 15 Newton, and the z-axis will be 100 Newton. So here the arrow show that the bearing load apply here, and make sure that we come to below. And then the cylindrical support applied with these 2 surface inside. That's why we be bearing load here to make sure what will result on here after this. So the bearing load that we apply here is very traditional, will be the free, because we want to make sure that this component, when the bearing load apply here to downside, it will make sure the tragedy will come to fronts like that. So finish for the static structure, and the solution, we find total deformation. Okay, total deformation, here's some movement. So the bearing load apply here, and the stress deformation will be applied here. And here the equivalent stress also at the side of the material, and the highest one will be 9.7 Pascal. So next will be the safety factor and safety factor ratio. So this one will be the material of stainless steel. So the stress ratio will be 0.004%. So the application highest impact on here, because the applying load makes this region become more impact. So after finish all the stress and the static structure, we apply topology observation, and here the insert the material, and then the region, design region, extrusion region, because the cylindrical support and bearing load here. So for objective is follow the software static, and then here the response constraint we set about 80% of mass. And then the last thing will be the objective and all response components, the graph, and the response constant mass. And lastly will be the topology density tracker. Here there's an example. So I mean focus for steel, stainless steel structures, and they have three. So I just focus for metrology. I just focus structure steel. Here the topology density tracker. That will be the topology optimization apply. So this one will be 80% remove. And here the topology, the video, the process of the topology observation, capture here, and make a new redesign. So that's it for the methodology for chapter 2.
Hello everyone, my name is Mohamad Hadiman bin Hamim, and I will present about the result and discussion. The first discussion we will discuss is the equivalent stress analysis of von Mises stress. Von Mises stress is equivalent stress analysis is technique used to calculate the maximum stress applied to a part design, and it also to ascertain whether the part will yield following the material constant imposed on the region. As you can see, this is the result of equivalent stress analysis that we run on MC software. So this is for the stainless steel, this is for the structural steel, and this is for the titanium alloys. Based from the result of the NC software, we tabulated the equivalent stress of the three material. The minimum value for the three material is the titanium alloy, which has the smallest value, which is 5257.2, and the maximum value for the three material is also from the titanium alloy, which is 947,601 times to the power of 5. Next, we will talk about total deformation. Total deformation is the significant number that refer to a system directional deformation along a particular axis resulting from the loading that result in a change in the shape of the part design. Based on the NC software, this is the total deformation of the stainless steel. This is for the structural steel, and this is for the titanium alloy. Based on the NC software, we tabulated the total deformation of three materials. For the minimum value of the three materials, the smallest number is from the structural steel, which is 4.70009 times 10 to the power of -5. For the maximum value of the three materials, the biggest number is the titanium alloy, which is 6.1185 times to the 10 power of -3. Next, we will discuss about the safety factor. The safety factor is essential to know if the product is safe to use or not. By calculating using the formula of allowable over applied force. For the safety factor, it must withstand more load than the load in the simulation. This is the safety factor of stainless steel from the NC software. This is for the structural steel, and this is for the titanium alloy. From the NC software, we tabulated the safety factor of three materials. The minimum value of the three materials The smallest value is from the stainless steel, which is 0.20735. And for the maximum value, the three material has the same value. That's all for me. Thank you.
Hi, my name is Mohamad Faiz bin Hamzan, and now I will continue about the redesign the model after the optimization analysis have been done. The topology optimization analysis can reduce the mass of the model. So this background level can reduce to 80%. For structure steel, stainless steel and titanium alloy have no much different reduced mass. The topology optimization analysis has been doing in ANSYS software to determine the optimum shape. The bell crank lever will redesign use the topology optimization result as reference. The new design will simulate at 3D printing software to determine the overall duration, which is the overall duration is 7.5 hour for about 230 grams. This is the objective and mass response convergence graph. As you can see, there are three types of material. Those three type material have the same pattern: the structural steel, stainless steel, and titanium alloy. Also, for the objective and all response convergence, those three material has no much different of its pattern. So for the conclusion, this background level topology optimization was analyzed by three types of material, which is stainless steel, structural steel, and titanium alloy. This can be accomplished by using SolidWorks for design and Workbench ANSYS software for doing analysis. And we analyze in terms of equivalent stress, total deformation, and safety factor. There is no significant difference between the value, the maximum and minimum value for all material, like my friends present in previous video. However, structural steel was selected due to its maximum total deformation, which is the lowest among other materials. FEA process is completed. The bell crank lever's design was analyzed by using topology optimization to determine the optimal structure for the model design. Optimization for the invention is required to lower the mass of the model and the printing time. By minimizing these two parameters, production costs can be diminished and the model can be made with the best design possible. This optimization process was repeated 3 times to select the optimum percentage decrease among the 3 results with 3 times. And the objective by comparing material, lowering the mass density and redesigning the frame was effectively accomplished. That's all from me. Thank you.